Salam and a very good day. We are Team 1, supervised by Dr. Nahuda, and the team members are Izzah, Mardia, Akila, Fazrin, and Ain. We'll be presenting on our project, Production of Acetone from Propylene. Process flow diagram begins with a basis of 100 kmol per hour of propylene and excess water enter the first fixed bed reactor, where sulfuric acid comes as a catalyst to achieve quick conversion and produce isopropyl alcohol, IPA. Next is a heat exchanger to increase the temperature before enter a distillation column to separate about 90% of propylene. And then next is a heat exchanger and a compressor to increase the pressure before enter the second fixed bed reactor with copper zinc oxide as catalyst and produce acetone, hydrogen, and other components as well. So this reactor converts the IPA at the rate of nearly 90%. Then there are two heat exchangers before enter the flash column and separate liquid and vapor substances. And then the top of the flash column enter the absorber with water as an absorbent and separate a huge amount of hydrogen. The bottom mixed with stream 11 before enter a heat exchanger and a valve to reduce the pressure, then separate the components to get the desired product, which is acetone with 99% purities at the top stream of the distillation column.
Thank you, Fajrin, for the input. My name is Izzah Nazira, and I'll be explaining more on the mass and energy portion of this presentation. So the law of conservation of mass states that in a chemical reaction, mass is neither created nor destroyed. So this means that the input plus generation minus the output and consumption is equal to accumulation. And this general mass balance equation is applicable to every single unit operation in the plant. Next, we'll look at the mass balance for a fixed bed reactor. In fixed bed reactor 1, the assumptions are that the system operates at continuous steady state, side reactions are negligible, perfect mixing and constant densities of components are expected, and the unconverted components will exit from the reactor together with the products. Next, for fixed bed reactor 2, the assumptions are the same. Next, we'll look at the mass balance for distillation column 1. In distillation column 1, the assumption is that the process is a continuous and steady state process in which the column efficiency is 99%. We also selected the light key component and also the heavy key component of this distillation column according to the component volatility. So the selected light key component in this distillation column is propylene, while the heavy key component selected is water. The Xi for light key and Xi for heavy key are 0.99 and 0.01 respectively. For distillation column 2, the second distillation column, the assumptions are similar, in which the process operates at continuous steady state with column efficiency of 99%. However, in distillation column 2, the light key component is acetone, meanwhile the heavy key component is isopropyl alcohol, with Xi being light key, Xi for light key being 0.99 and Xi for heavy key being 0.01. Next, we'll look at the extended calculations for distillation column. We first calculated the vapor pressure calculation using the end Planck constants. We also had to use another calculation for vapor pressure calculation of hydrogen using the Clapeyron-Clausius equation as shown on screen due to the temperature constraints. Next, we calculated the relative volatility. After calculating the relative volatility, we then calculated the split fraction using the Franski-Underwood-Killian shortcut method. After finding out the split fraction, only then we calculated the molar flow rate and also the mole fraction for both the distillate and also the bottom stream. Next, we'll look at the mass balance of the absorption column. In the absorption column, it is assumed that the process operates at steady state with recovery efficiency of 0.99. The key component is acetone and the system is said to be isobaric and isothermal. Next is the determination of the theoretical stage of absorption column. So by plotting a graph in Excel of the mole fraction of acetone in the air against the mole fraction of acetone in water, we then determine that the theoretical stage of absorption column to be 5. That's all for me. I'll pass the presentation to the next presenter.
So for the mass balance of flash column, the assumptions are the light key component is hydrogen, which is about 0.99. The heavy key component is isopropyl alcohol, which is 0.01. And the efficiency of the column is 99.99%. For the mass balance of auxiliary equipment, we'll be using the law conservation of mass, which is input plus generation minus output minus consumption is equal to accumulation. This type of mass balance is applicable in all auxiliary equipment streams. Next, for the energy balance, we'll be using the first law of thermodynamics, which is net energy transferred to the system is equal to final system energy minus initial system energy, which is first reference temperature and pressure at 25 degrees Celsius and 1 atm respectively. The system is at steady state and all of the components are behaving at ideal condition. Heat capacity of each component is only function of temperature, and heat of formation of each component is referred to its phase at reference state. And lastly, pressure-based enthalpy changes are neglected. For energy balance calculation, we'll be using specific enthalpy calculation. Also, we'll be calculating the specific enthalpy calculation for each component. And the calculations were obtained from Paris Chemical Engineering Handbook. And lastly, the calculation of total enthalpy with and without phase change.
Hi, I'm Nadia and I will explain about simulation pipe. So this figure shows the overall equipment used in AVEVA Pro 2. It consists of 14 equipment, 2 equilibrium reactor, 5 heat exchanger, 2 distillation column, 1 compressor, 1 flash separator, 1 absorber, 1 mixer and 1 valve. The thermodynamic use is ideal 01, which means ideal, and also flow basis input is in k mole per hour. So this slide shows the comparison between manual calculation for mass balance, and this is for stream 1 to stream 10. For stream 5, we can see the deviation is quite high, which is 20.57%. And this is the comparison for stream 11 to stream 20. So almost all the stream has an error less than 20%. So 1 out of 20 streams have deviation exceeding 20%, which was S5. So S5 coming from the distillation column 1, which is the distillate stream. So the error might be due to the output value from the reactor. Actually, the actual reactor that was supposed to be used was a fixed bed reactor, but there was no fixed bed reactor in AVEVA Pro 2, so we decided to use an equilibrium reactor as an alternative to replace it. The outlet value of reactor outlet of distillation column 1, including the mass balance calculation, was affected by this problem. So this is the comparison between manual and simulation calculation for energy balance. This is for stream 1 to stream 10. Here we can see the deviation for some stream are more than 100%. And this is just comparison of stream 11 to stream 20. Some of the stream have errors exceeding 100%. So here are the justification for the energy balance. For distillation column, it involves stream 4 and also stream 5. So there should be a huge amount of propylene to be exited from the stream 5 at the distillation column. However, the amount exited is not like what we expected. And also, there are some temperature difference between simulation and also actual temperature. So if we try to change the temperature, the simulation cannot be executed. So for stream 8, 9, and also 10, it is related to the reactor. So there is no fixed bed reactor in AVEVA Pro 2 simulation. So we use an equilibrium reactor as an alternative to replace it. For stream 11 and 12, it related with the flash column. So the problem of this stream is because of the huge amounts of water coming from the reactor 1 has been carried out. So all this happened because there is no evaporator that can be used to evaporate the water from stream 2 in the AVEVA Pro 2. So for stream 14 and also 15, it related with absorption column. So there is no absorption column in AVEVA Pro 2 simulation. So we use the distillation column without a reboiler and condenser as an alternative to act as an absorption column. So this may affect the results of this simulation process. So the height deviation in stream 18 is because of the distillation column. So there should be a small amount of hydrogen and also acetone to be vented out from the distillation column. However, in simulation, it follows the concept of distillation column. All components will be condensed. So that is why the purity of the product is affected. And also there are some differences with actual temperature and also simulation temperature. So if you try to change the temperature, the simulation cannot be executed. So as a conclusion for energy balance, what we can summarize is that the height deviation is due to the limitations of the AVEVA Pro 2 itself. So we confirm that manual energy balance calculation is the correct one because that one is follow the theoretical and also fundamentals of energy balance. But for the software, the limitation itself where certain unit operation are not available in AVEVA Pro 2. So we are unable to reflect the actual unit operation in the actual calculation and the unit operation in the actual plant. Because of that, it will affect the operating temperature used in the manual calculation and in the Aviva Pro 2. So if we use the actual temperature, the simulation cannot be executed. We have tried the simulation for many times, try and error and playing with the temperature and so on, but the issue is we are unable to converge the simulation flow sheet. We have tried our best, but still cannot converge. So at the end, we come up with this flow sheet and we managed to converge it. This is all what we have done for mass and energy balance. Thank you.
In this effluent management, we are going to talk about three types of waste, which are solid, vapor, and liquid waste produced in this production plant. The solid waste generated from this production plant is copper zinc oxide catalyst from reactor 2. There are two methods proposed in order to manage the solid waste, which are catalyst regeneration and disposal through scheduled waste. Both methods have their own pros and cons as presented in this table. So after going through both the advantage and disadvantage, our company chose to dispose the spent catalyst through disposal through scheduled waste. Disposal of scheduled waste offers a more economic option as it eliminates the needs for an on-site treatment facility to be built, hence cutting some costs. Spent catalyst copper zinc oxide is labeled as SW202 under the category of solid waste for scheduled waste to be handled accordingly under Section 34B of Environment Quality Act 1974. The catalyst will be sent to Quality Alam Sdn Bhd for disposal. There is only one vapor waste produced in this plant, which is propylene that generated at the upper stream of distillation column 1. There are several methods to manage the propylene waste, which are reuse or release of the propylene waste to the environment. Listed here are the summaries of the advantage and disadvantage for both methods. We decided that the best alternative is to release the propylene vapor to the environment since it's safe as it does not give any harmful effect on the environment, human and animals. Although propylene vapor is very useful in petrochemical industries, the composition of the production of propylene in this plant is quite low, which is 581.062 kg per hour, compared to demand in industries of petrochemical with 97,433.86 kg per hour.
There are three alternative treatment types: chemical oxidation, membrane separation, and distillation, with the advantages and the disadvantages as stated as in the table. We decided that chemical oxidation is the best treatment among these three due to its benefits, more efficient, cheap, and eco-friendly in the degradation of any kind of toxic pollutant. So advanced oxidation process, AOPs, is the treatment that we use to treat the wastewater as it can degrade the organic compounds, which are isopropyl alcohol, IPA, and the acetone. So this treatment can remove contaminants, and the UV that used in this process is the most effective in eliminating 99% of organic compounds in contaminated water. This treatment process involves several steps, where in the last step, we'll be producing water, carbon dioxide, and inorganic salts.
After the liquid waste treated through advanced oxidation process, our company discharged the liquid waste generated from the plant to the environment. According to the Contaminated Land Management and Control Guideline 2015, acetone discharge must not exceed the daily limit of 1.4 mg per liter, and the maximum exposure limit of isopropyl alcohol is 0.041 mg per liter. So far, there is no standard value for acetone and isopropyl alcohol discharge set by Department of Environment, DOE. So we considered the standard values from Contaminated Land Management and Control Guideline 2015 as an alternative to be our guideline in order to discharge the wastewater. That's all from us. Thank you.